here I have an inductor connected to an AC source, just like that. And so there would be some AC voltage, an alternating voltage being applied to the inductor, and that would obviously generate a current in this, an AC current in the circuit. And let us have a look at how all that thing happens, right? So first of all, we are assuming that the whole circuit, including the inductor, has a very small or negligible amount of resistance, and such a circuit which only has an inductance associated with it due to the inductor and has no resistance or negligible resistance and no capacitance for now is called a purely inductive circuit, because it only has some inductance and it has no resistance or capacitance, right? So this is a purely inductive circuit here, and we've connected this to an AC source. Now first of all, because this is a loop here, we can use Kirchhoff's loop rule, which states that the potential drop across along a whole along a complete loop should be zero. In other words, the energy gained by the electrons at the source, at the energy source, that energy or that potential has to drop throughout the whole loop, throughout the whole circuit, as the electrons travel from one terminal to the other terminal, right? So let's say if the source voltage at any given instant is, let's say, 3 volts here, so the that means that the electrons gain 3 joules. Every coulomb of charge gains 3 joules, and that coulomb of charge has to lose those 3 joules as it travels across the whole loop, across the whole circuit, right? So now we can write an equation for that, which is the source voltage should equal the drop in potential. Now the problem here is that we don't have any resistance, so there is no heat loss in the form of, I mean, there is no energy loss in the form of heat due to due to resistance, because there is no resistance. This is a purely inductive circuit. There is no resistance, so we cannot use Ohm's law to find the potential drop across these wires because they have no resistance. So there is no drop across these wires. So where does all that energy go? Well, all that energy gets stored in the form of magnetic potential energy in the field lines, in form of the field lines of the inductor. So as current passes through the inductor, the field lines of the inductor get stronger and stronger, and the energy gets stored in the form of magnetic potential energy in the inductor, right? And what we can say is the potential drop across this inductor would be equal to the back EMF generated, and well, we have an expression for that, which is the inductance times the rate of change of current through the coil, through the inductor, right? And yeah, this is the back EMF, or the induced EMF in the inductor, and that should be equal to the source voltage, because so that the complete drop in the whole loop is zero, or rather the energy gained, the potential gained, is dropped across the whole circuit. Now that is the expression that I get, and if I move further ahead, I can write this as, actually I can shift the L from here to the other side and write it this way, right? And what I get is V upon L equals di by dt. I think it will be clearer if I just switch the sides. It will be easier for you to visualize, and so I take it on the other side. This whole thing equals V upon L, right? Yeah, and now to find the current to the whole circuit, what I need to do is I need to integrate both sides, because here I have the rate of change of current. So to go from the rate of change of current to the actual current, or rather to find the actual current, I need to integrate both sides, right? So what I do is I say the integral of di by dt with respect to dt, right? I'm integrating with respect to time here. that equals the integration of the voltage, source voltage, divided by the inductance with respect to dt. Now here obviously if I have the rate of change of current and I'm trying to find the if I'm trying to integrate the rate of change of current, I should obviously get current. Or if you want to go a bit mathematically, you can simply cancel the dt and the dt, a small change in time, a small change in time. You can cancel those two small changes in time and you get here integration of di, or rather the sum of all those small di's, all the small changes in current, and what you should get is the total current, right? So here the integration of di is simply I, or the total current, and that equals the integration of v by L dot dt. Now I know that this is an AC source, so the voltage must be alternating, and I have an expression for that alternating voltage. What is that? Well, that is simply Vm, the peak voltage, times sine omega t, right? That is the expression for voltage, the source voltage, and obviously I have this L in the denominator, and it's being integrated with respect to dt. I hope all that is visible easily. Yeah, so now what I can do is I can simply start integrating. Now I know the Vm and the L are constants, so I can pull them out of the integral symbol, and I'm running out of space. So what I will have to do is I'll have to just remove the starting step and continue here, obviously. Yeah, so what I'll do is I hope that's visible. Yeah, so I know that the current equals, I'll pull the constants out, Vm upon L, and I'm left with the integration of sine omega t dot dt. And well, I can write that as I equals the union, yeah. Now the integration of sine of something with respect to dt would be, so I won't get into the details of it, or else it might confuse you. I'll just state it. It so happens, so just because some of you are not so comfortable with integration, so those of you who are comfortable with integration, you can do this nicely, understand this nicely, but I won't get into the exact step here. I'll skip it and tell you that if I integrate this thing, what I get is I get here 1 by omega and cos omega t, yeah, and obviously we also get a constant of integration plus c, but in this particular case the constant of integration would be 0. Well, the reason for that, well, if I can just quickly give you an intuitive reason for that. So if I just plot the so this is the current, right? Now we know that the voltage in an AC source oscillates along about the 0, right? The mean value of an AC voltage is 0. So the voltage increases from 0, goes to positive value, comes back to 0, goes to some negative value, then comes back to 0, then goes to some positive value, and so on and so forth. Now it is obvious to us that the current should also oscillate about this mean value, which is 0, right? It should also oscillate this way. I mean, the magnitude and the phase can be different, but it should also have a mean value of 0. So the current should start at 0, go to some positive value, come back to 0, go to some negative value, and so on and so forth, and the mean value should be 0. That seems intuitive. And if you think, what does this plus c do? What does this constant do? This constant actually shifts your graph up or down, and we don't want to shift our graph either up or down, because we want our graph, our current to oscillate about the mean value of 0, right? So we don't really want it to shift up or down, and for that to happen we want our constant to be simply 0. So we just don't want the constant to be there, it should be 0, right? So that's an intuitive idea of why the constant in this particular case is 0. I won't get into too much detail again here, and yeah, I'll quickly now wrap up. Now I'll remove all these steps here quickly. Yeah, so yeah, now I have got current equals this thing, and if I quickly just clear this up, now one small step right here which might confuse some of you. I hope you remember the identity that minus cos theta equals sine theta minus pi by 2, which is 90 degrees. I hope you remember this identity. I mean, you've done this identity in class 10, right? So I just hope you remember this. Now what I can do is, yeah, I'm not really sure about this negative sign here, but yeah, this is the identity that we can use right now here in this particular step also. Now to make this a bit more clear, I can write this as I equals Vm upon, I can just combine this omega with the L, omega L, right? These are the constants here, and instead of writing cos omega t, I can write this as sine omega t minus pi by 2, right? So I've just taken my omega t as theta, and I have used this identity. Now I'm not really sure about this negative sign here, really sorry, but yeah, this was the identity I used. I'll just mark it out, and this is the final expression that I am left with. So I'll just remove the steps here just to focus on the real final expression. And yeah, this is the final expression that I'm left with. The current in a circuit equals the peak voltage divided by the frequency times the inductance times sine omega t minus pi by 2. Now the things you need to note here is, what you can do is, so remember, this is of the form I, or the current at any point, equals some constant times sine and omega t minus pi by 2. Now obviously this constant here is the peak value of your current. So what I can write is, instead of writing this, I can write this in the form I equals the peak value of current, Im, times sine omega t minus pi by 2. Now we'll get into the details of what this pi by 2 mean and all that in the next video, but yeah, I'm just dealing with the mathematical part right now. I equals Im, peak value of current in the circuit, times sine omega t. So yeah, this thing gives you this expression gives you the current at any point at any instant in time, and by comparing these two equations, we can see that the peak value of current Im equals peak value of voltage divided by omega L. Now obviously I'm just taking one instant of the peak value of current and peak value of the voltage. This same equation can be written for any value of current and voltage, any corresponding value of current and voltage. So I can write this as current equals voltage upon omega L. But the thing to notice here is that this expression here is of the form, well, let me remove this. So I hope you're noting this side by side, because I'll keep on removing the steps. I don't have enough space to fit all that together. But yeah, this thing here is of the form this is of the similar form of Ohm's law, which is I equals V by R, right? This is Ohm's law, and so Ohm's law was applicable to resistive circuits where we only had resistances, but this expression here is applicable to circuits that have that are purely inductive, just like this here, that have only some inductance, no resistance, no capacitance. And if you see that this term here, omega L, is actually analogous or similar to this term here, called the resistance. And so you can imagine this omega L as this thing that is actually opposing the flow of current. Here resistance opposes the flow of current, and here omega L is opposing the flow of current. And so we call this thing here as, well, this, because this is an inductive circuit, this is called inductive reactance. I just hope that fits. Yeah, this is called the inductive reactance, and this is pretty much, you can imagine this has the resistance of an inductive circuit. So this is pretty much similar or analogous to the resistance in a resistive circuit. So you have resistance in a purely resistive circuit, and you have inductive reactance in a purely inductive circuit. And yeah, that's all there is to this video. This is the mathematical part that I wanted to cover. Now the next video we'll cover the intuitive part of all this and try to make more sense of all the equations and all that stuff that we've dealt in this video. That's for this video.